This video is about numeral systems, in particular about the binary and the hexadecimal system. Let's look at a normal number given in the decimal numeral system. So the number is 3746.56. So what do the positions of the digits stand for? Before and also after the decimal point. So this is nothing new for you. You know they represent a factor of a power of 10. So we can write this is 3 times 3000, 3 times 10 power 3, plus 700, 7 times 10 power 2, plus 40, plus 6 times 10 power 0, and plus 5 times 10 power minus 1, plus 6 times 10 power minus 2. So the two digits after the point have negative exponents. So this is a number with bases 10. So the base is 10. And the digits which are available are, we can use 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but not 10, because the 10 is no digit allowed here. This is then represented as 1, 0. So why does the decimal number system exist? The simple answer is because we have 10 fingers for counting. So in order to indicate the base, we use here brackets. We use brackets here and subscript 10, which indicates the base 10 in the decimal system. But it is also plausible to use any other natural number as a base for a numerical representation. For example, I just use any base 7. And how to convert this into decimal system as above. 4 times 7 power, so 0, 1, 2, plus 5 times 7 power 1, plus 1 times 7 power 0, plus 2 times 7 power negative 1. And if you calculate this, you get the result in the decimal system as a decimal number. So as you see here, the base is 10. Let me write it here. The base is 7. And the digits you can use 0, 1, 2 until 6. So in general, this means we have, in the decimal system, for example, we have 10 digits from 0 to 9. Here we have 7 digits from 0 to 6. In general, from 0 to b minus 1. So for bases, for a base which is smaller than 10, we can do it like here. If you have a base greater or equal to 10, we need new names or labels for the digits. And you will see this later. So then we will use letters like A, B, C, D. So before we come to that, we consider the so-called binary system. So here is the decimal. The next one is the binary system. This is especially important in computer science because the base is 2 and the digits are just 0 and 1, 2 digits. because this is what you can store in a transistor or represent using a transistor, off and on. So let us try an example. So this is a binary number, sometimes also called a dual system. And we want to convert it into the decimal system. So we have 0, 1, 2, 3, 4. So 1 times 2 power 4 plus 0 times 2 power 3 plus 1 times 2 power 2 plus 1 times 2 power 1 plus 0 times 2 power 0 plus 1 times 2 power minus 1, 0 times 2 power minus 2, and the last one, 1 times 2 power minus 3. So we calculate the number. So 2 power 4 is 16. The zeros we do not need to consider. Plus 4 plus 2 plus, this is 1/2. And in the decimal system we can write 0.5. 1 divided by 2 is 0.5. And the last one is here. So this is 1 divided by 8. 2 power 3 is 8. And 1/8. This is what the wine drinkers usually knows. The wine drinker usually knows it's 0.125. And if you summarize this, we get 22.625 in the decimal system. So we also know how to convert binary numbers into decimal numbers. Another important case, another important base in computer science is the hexadecimal system. In this case, the base is 16, so hex for 16. And we need 16 different symbols or digits. And the digits are not clear from the beginning on, so we have to define them. So from 0, 1 up to 9, okay, this is what we can already use. We have 10 digits, but we need 6 more, and we just use letters like A, B, C, D, E, F. And 10 stands, A stands for 10, B for 11, C for 12, D for 13, E for 14, and the last one for 15, which is again B minus 1. Note we cannot use 10 because 10 is already written in the decimal system, so we have to come up with a new variable. And we look at an example. FAD 0.9. We want to convert it to the decimal number system. And F, you look in this table, stands for 15. Then we have here 0, 1, 2, so 16 power 2. A stands for 10. D stands for 13. Plus the digits after the point is just 9, 16 power negative 1. If you calculate this, you get the number in the decimal system. So this is the procedure how to convert numbers with the base b. So we have used 7, 2 and 16 into the decimal system. Now let's look at the reverse direction. A decimal number is given and it should be converted into a binary or a hexadecimal number. And we just start with an example. Let's see if I have enough space here. I start with 77 in the decimal system and I want to convert it to the binary, a number in the binary system. And for this you can use the so-called division algorithm. So first let's make some space here. So now we have enough space that I can show you the so-called division algorithm. So you write the number 77 here. You create a line, a vertical line, and you divide by 2. 77 by 2 is 38, and the remainder is 1, which you write here. 38 divided by 2 is 19, the remainder is 0. 19 divided by 2 is 9. 2 times 9 is 18, remainder 1. 9 divided by 2 is 4, remainder 1. 4 divided by 2 is 2, remainder 0. 2 divided by 2 is 1, remainder 0. And the last one, 1 divided by 2, it's not possible, so the remainder is 1. What you do now is you read the number from the bottom up. And that is the number in the binary system. So 1, 0, 0, 1, 1, 0, 1. The question is, why is this the case? And in order to understand this, you represent this number 77 using powers of 2. So you can use this binary number and represent it in the decimal system. So we actually do what we had done at the beginning. We convert it back to decimal. So this is the number 77. So what did we do actually? So I just shifted a bit to the left. What did we do in the division algorithm? We divided by 2. And we write down the remainder. So if we divide this summation by 2, you just decrease the exponents of these powers. If you divide by 2. It's a lot to write. And the last one would be 2 power minus 1, but this is what we actually used as a remainder. So we use the color here. So the 1 here was written to here. So it's this remainder. And you can imagine that you can repeat this procedure. And the next remainder you can read here. It would be this 0. So you can see it here. And the next remainder is here if you do it again and again. So it's here. So you see, the division algorithm obviously works. So up to now we converted integer decimal number 77. But what is if we want to convert decimal numbers with digits after the point? And I just show you an example. So we want to convert 0.3. Maybe let's start here. From the decimal system into the binary system. So in this case, we do something similar to the division algorithm, the so-called multiplication algorithm. We start with 0.3. You create a vertical line and you multiply by 2. So it's 0.6. And now you consider the so-called borrow, or you can also say carry over. So here it is 0. Because the number is less or equal 1. The borrow would be 1 if the number here is greater than 1. So let's go on. 0.6 times 2 is 1.2. The carryover here is 1 because the number is greater than 1. But you continue now. You continue to calculate with 0.2 because you have written the 1 here. So 0.2 times 2 is 0.4. No carryover. Times 2 is 0.8. No carryover, which is 0. Times 2 is 1.6. Carryover is 1. You continue to calculate with 0.6 times 2 is 1.2. Carryover 1. 0.2 times 2 is 0.4. Carryover 0. So you could go on and on. But what you see here, that we had 1.2, we had it before. So the digits are repeated. So we have a period starting at 1.2. So the period starts at 1.2 here until here. So it is obvious that we have a 4-digit period, and we can write down now the number in the binary system here. So 0 point. The first one is 0 is here, and the next one is 1001. So the 4-digit period is indicated with an overline over these four digits. So what does this mean? This means, if you would write it out, that this is repeated infinitely often. So let's write a few. 0.0, 1001, 1001, 1001, and so on. Good, so that's all about converting from decimal to binary numbers. What remains is we would like to convert a decimal number into a hexadecimal number. Essentially, the division or multiplication algorithm would also work, but the division or multiplication by 16 is quite cumbersome or time-consuming if you do it manually. So it is simpler to first convert the decimal number into binary numbers and then convert directly into hexadecimal number. Why is this easy to do? Because 16 is a power of 2. 2 power 4 is 16, you know this. So this means that 4 digits in the binary system correspond to 1 digit in the hexadecimal system. So let us show you. We use the fancy color now to indicate that. We start from the right of the point. So here is this example 77. From the right of the point, there is no point actually, and we create blocks of 4 digits. So this is the first block of 4 digits. The next one only has 3. If you want, you can imagine here a 0 also. And how to convert it now into hexadecimal? The first number is 0100. So first you convert 0. Where should I write it? Maybe here in the bottom right. You convert 01. You convert it into the decimal system, and this is 4 in the decimal system. And this is the same number in the hexadecimal system, so you can write 4. The next one is 1101. This is 1 plus 4 is 5 plus 8 is 13 in the decimal system, which is the letter D in the hexadecimal system. So this is just 4D. Is it right? 1, 5 plus 8 is 13 should be right. Okay. In the second example, on the right side here, you need to write the periodic digits until you recognize the period in the hexadecimal system. So you create blocks of 4. Okay, the next one, and you see here in the third block already it starts repeating. Yeah, so that's enough. And we start, I have forgotten to mention that we start from the left of the point. We always start from the point. So let's write this as 0 point. The first one is 0100. We also had it here. This is 4. And then 1100. First in the decimal system, which is 4 plus 8 is 12. 12 stands for C. And the C is repeated infinitely often. Don't forget to indicate the period with this overline.